So good morning. This is going to be a relatively fast-paced introduction to machine learning for everyone. You don't have to be a developer. You don't have to know a lot of math. We will talk about the math, but I'll try to make it kind of approachable. But today, as Matt said, this is going to be the first part of a two-part talk. The first part is going to be the what and the how, and then we'll get into the why and the so what in the next section, along with a lot of practical applications. So who's excited? Yeah. Okay, first of all, what is machine learning? Let's figure out what machine learning is. So let's say that you want to train a computer to play rock, paper, scissors with you. You have a computer with a camera, it's taking images, you hold out a hand to the computer screen, and you want it to be able to tell you if that's rock, paper, or scissors, and then you want to be able to play a game with it where you throw and the computer throws and you see which one wins. Well, this is going to be kind of an interesting challenge because, first of all, you have to teach the computer how to identify a picture of a hand. How would you describe a hand? Okay, well, let's see. Maybe we could say we'll look for the pixels in this image that are flesh colored. Well, but skin comes in a lot of different colors. And what if they're wearing hip fingerless gloves? Or what if they're underneath a blue light or a red light like this is? Then the skin is going to appear different colors that aren't skin tone. And as you can see in this, there's, I mean, this is obviously a Photoshop corrected image, but there's a lot of variance in the colors. So, okay, let's look for fingers maybe. Well, what if the hand is a fist? How would you describe a finger to a computer? Maybe we could look for the edges. Well, what if there's a whole bunch of other hands and other skin in the background of this, or they're holding the hand over their arm, or maybe the image is slightly blurry because it's out of focus. This is really difficult. Oh my goodness. How do you describe this to the computer? So this is where machine learning comes in. Machine learning has been designed to solve this problem. Traditional programming, you create the rules, the functions, and you pass in data, arguments, and you get out answers, results. Machine learning flips this on its head, where you're passing in data and answers, basically labeled, structured data, and you're getting out the rules in the form of a mathematical, statistical model. So before we go further, let's try this out. And if you have a phone or on your computer, you can go to this address and test it yourself. But we're going to go to something from Google called Teachable Machine. And this is the first version of Teachable Machine. And we're just going to jump in and skip the tutorials. OK, so I need to let it use my camera. And hello, hopefully you can see me on this. So first of all, let's see, let's train it with scissors. And so I'm going to step out of the frame here. I'm going to hold it down, and I'm going to move in different positions so that it gets lots of different training data. OK, and so now when I'm holding up scissors, 99% confidence. It makes an inference, 99% confident it's scissors. But unfortunately, it has no other data. It has no background data. So it thinks everything is 99% confident scissors. OK, so let's train it with a rock. So hold up a fist in front of it, turn it to the side, turn it there, put it up to the screen like this. OK, so now holding up a fist, 99% confidence, it's a rock. Hold up scissors. And whoa, OK, we're still getting some issues. And so you can see this is a little bit hard. Now let's see if I train it with just background noise to kind of differentiate that. I'll move out of the picture and move in the picture. OK, so right now, orange, it thinks that there's nothing going on. Hold up scissors, and we've got really good confidence. Rock. OK, what if I hold up a hand for paper? Oh, it thinks it's a rock. It thinks it's scissors. It doesn't really know. So this gives you the basic idea of how machine learning works at a very, very rudimentary level. We are taking in a lot of samples of data. We're telling it what is green, in this case, scissors, what is purple, in this case, a rock, and what is background noise. And it's giving us an inference, a confidence, a statistical confidence on what's there. OK, so what we're going to cover today, again, going to move this through this really quickly. We just talked about what is machine learning. We're going to talk about how machine learning works next, how we can use it, and then where you can learn more. And next time in 2 weeks, we'll talk about what we're going to be covering there. So how does machine learning work? I will probably go a little bit fast. If I am talking too fast and you can't understand what I'm saying, please let me know. But before we begin, is artificial intelligence machine learning? Is machine learning artificial intelligence? You might see them used interchangeably, but AI is not machine learning. AI is kind of an umbrella term. Machine learning is one of the algorithmic techniques for implementing artificial intelligence. Artificial intelligence as a field has been around for a really long time, and there are a bunch of different approaches. Machine learning is one specific approach that has become very popular for reasons that we'll get into a little bit later in this talk. Another sidebar on this is that I gave a version of this talk at a hackathon for Valtech in January, and the one question that I got from everyone is, should we be afraid of Westworld robots coming to kill us all? And there are a lot of things to be afraid about when it comes to machine learning, which we'll get into in the next talk. But by and large, we're not going to have artificially intelligent robots anytime in the near future. In the words of Maeve from Westworld, really, darling. So AI not equal to machine learning. You may see AI used as an umbrella term. Sometimes people use AI interchangeably with artificial general intelligence, which is the ability for a computer to reason without context of a specific domain. But machine learning is one that works really well because it has a specified domain. It has a limited context. And as you saw when we did our example with rock, paper, scissors, you held up a hand or some kind of gesture that wasn't recognized from what you had trained it on. It didn't know what to do. So the steps of machine learning, according to Yifeng Guo from Google in a great YouTube series, are first you have to gather the data. You have to assemble all of the data in your domain that you're working with. Then you have to prepare it because the computer isn't really going to understand things. So you have to put it into something that can be turned into numbers. If it's text, you have to process it in a way that all of the words can be turned into numbers that can then be evaluated. If it's an image, it's going to be turned into pixels. If it's audio, it may actually be a bitmap of the waveform so that it can process that bitmap with the same kind of image processing stuff for reasons we'll see in a second. Then you need to choose what kind of model you want to use for doing this machine learning. Then you need to train that model, evaluate how well it did, and then tune the model based on how well you tested it. And then when you finally tuned your model to be really good, you want to make predictions. You want to make inferences when it sees data that it hasn't seen before. So there are many different types of ML models. Support vector machines, decision trees, or when you have a bunch of decision trees, decision forest, genetic algorithms. And the one that we're going to be focusing on today is artificial neural networks. I'm happy to get into any of these in the Q&A at the end, but by and large, when you hear machine learning, people are talking about neural networks. Now, when we talk about a neural network, are we talking about actual wetware? Are we talking about biological cells, neurons that are connected to a computer? No, we're not. We're talking about, in the words of one Google engineer, a rough mathematical cartoon of how a brain works. And that usually is set up with a bunch of different nodes, and those nodes are arranged in layers. And on the far left side, what you can see here is we have the inputs. So let's say that these inputs are one node with a pixel value. Let's say it's a monochrome image. We've got a pixel value from 0 to 255, and that is for every pixel in the image, we have an input. And then on the other side, we have outputs. We have the classifications that we want to identify. So in this case, rock, paper, and scissors. And what we want is we want those classifications to be like a 100% confidence, like this is a rock, it's definitely not paper, it's definitely not scissors. And then in the middle, for a deep neural network, you have what are called hidden layers. And these hidden layers, the way that things work in this is that each node takes in all of the nodes from the previous layer and creates a weighted sum. All of those values are called activation values, and they're given a weight, and they're put together in some kind of formula, some function that is added with a bias, B, and that creates a new number that is the new activation value for that layer. And hidden layers can have a lot of different functions. One of the breakthroughs in recent convolutional neural networks is that the hidden layers can actually do a bunch of operations on the data to kind of clean it up and make sure that they understand it better. So convolution is a term for a calculation that's done in linear algebra with a big mess of numbers. Basically, the thing you need to remember is a convolution is essentially a Photoshop filter. So a convolution could be done on a hidden layer in each of these nodes that is detecting one specific piece of a picture that it's looking for. So if you're looking for hands, maybe a convolution is looking for fingernails, and it's highlighting all the pixels that are fingernails so that you can see the curve of the fingernail and see if the proportions of the distances between the fingers look about right. And then after a convolution layer, usually what you have is pooling, where it shrinks down the image by a quarter by taking the max value from every 4 pixels, and that usually ends up sharpening the image by improving the contrast. So you have convolution, and then you have pooling, and those convolution layers can look for all sorts of features. You could have one convolution function that's looking for straight edges that are horizontal, one that are looking for straight edges that are vertical, ones that are looking for different features of the hand. And then when you get to the end through all the hidden layers, this is a simplification, you have these things create their weighted sums to produce the outputs. And hopefully you're getting something approaching what you want for rock, paper, and scissors. And in early neural networks, they use something called a sigmoid function. Again, this is just to introduce you to the terminology of neural networks. So if somebody's talking about this at some kind of conference, you can be like, I know what that is. Sigmoids aren't used so much anymore, but sigmoids will squish all the data so that it fits between 0 and 1 so that your value is a neat 0 to 1 value. But that takes a lot of computational time. So for convolutional neural networks, one thing that you'll see that they use is rectilinear unit functions, or ReLUs. And ReLUs basically chop off everything below 0, everything that's a negative number, and say that's 0, and everything above it is positive. And so you're just looking for, like, is it positive and how much, or is it negative? Ignore it. And so, yay, you made it to the end of this neural network through one image. You passed one image into the inputs and you got outputs. But how correct was this? You have the answers, the data is labeled, so you know that this was supposed to be scissors or supposed to be rock. How are you going to figure that out? Are you going to do this manually? Or are you going to go back and tweak all of the values and nudge all the nodes in this neural network by yourself, by hand? No, you're not, because you're lazy, especially if you're a developer. You're lazy, so you're going to want to try to automate this. But how do we automate this? The key to figuring this out is to remember that this neural network, this model, is a giant mess of numbers. And before I go on, let's talk about numbers. I know, you're really excited about numbers. Well, if you remember anything about math or programming, there's single values. Single values are often called in math scalar values. And then you have vectors, which are basically an array of numbers, a list of numbers, like a coordinate system. But then you can get into higher dimensional lists of numbers, like a matrix, where it's 2-dimensional. Or you could have a stack of matrices where it's like three-dimensional, n-dimensional. It starts to get hard for you to imagine. And in programming, these are all really familiar. But in math, there's a term for all of these, and that's tensor. A scalar number is a rank 0 tensor, a vector is a rank 1 tensor, and a matrix is a rank 2 tensor. So these giant messes of numbers are tensors. And hey, achievement unlocked. Now you know this is why Google's machine learning platform is called TensorFlow, because it's a flow of tensors, big bags of numbers going through states and being manipulated. Anyhow, linear algebra. I promise we're almost through the math part of this, but there's a lot of linear algebra and calculus involved in this. There's a great link in the slides, which I'll share after, from Nikki Case. It's an interactive visualization of matrix math that shows how all of these calculations are done and why they can be done kind of quickly. So you want to aggregate all of these numbers in this giant model as tensors, and then you want to figure out what the differences are from where it should be so that you can nudge those values. And to do that, we use a differential equation called a cost function. That little upside down triangle is a symbol for the gradient. So if you studied any kind of calculus or geometry, the gradient or differential equations derivatives are used to figure out the slope of a curve, to figure out like which direction and how much you need to go to get to the next point in a curve. And these big messes of numbers are actually kind of multi-dimensional space. And so what we're doing is, if you think of this as some big curvy plane, we're trying to find the local minimum or the local maximum to get as close to 0 or as close to 1 as we can in this. And so this gradient function, this differential, tells us how much to move and which direction to move in that multi-dimensional space to get to the next step so that we can be a little bit closer. And it tells us how much to nudge those values. And so we figure out how to nudge those values. We pass those back up through the entire neural network model, and that is called backpropagation. So let's recap really quickly. We got the inputs, we did convolution, we did pooling, we passed them through a bunch of hidden layers, we processed them, we got to outputs, we got the gradient descent, and we figured out how much to nudge all of the values. We nudged all the values in one layer, then that made us figure out how to nudge all the values in the next layer, backpropagated it all the way to the beginning. We're at the beginning. Then we get the next image and pass it through and do the same thing for every image that you have in your data set. Well, actually, that's not exactly true. First of all, you're training your machine learning model on probably 70% of your data, because you don't want to overfit it so that it only recognizes things that are in your data set. You want to save 30% of that data so that you can feed it to it later, so that it sees things that it's never seen before, and it's like, I predict this is this, and you can be like, no, you messed up. Let's go back through and train again. And each time that you run through an entire set of the data is called an epoch. So if you see epoch, as you will in one of the future screens, it means we got through this whole large set of data. At this point, you probably have a lot of questions. I know I certainly did. So first of all, how do you know how many layers to put in your neural network and how many nodes to put in each layer? This is a really good question. And it turns out that this is sometimes as much of an art as a science. So TensorFlow has an open source library called Keras that's used for making it easy for programmers to establish a convolution layer or a pooling layer and just set up a neural network of a certain number of nodes. But then the act of figuring out how many layers and how many nodes are in that is called hyperparameter optimization. And when we talked about tuning that model, that's hyperparameter optimization, where you're figuring out the hyperparameters, the number of nodes, the number of layers. And the way that that's usually done is by death matching a bunch of different models against each other, which can take some time. And so sometimes people are even turning some of these into, they're making machine learning models that will tune their machine learning models, which is kind of. Number two, why is everyone all about machine learning and neural networks right now at this moment in time? Well, machine learning has been around since the late 1940s and the 1950s. You can find academic papers on it. It didn't really take off as an AI approach until the 1980s when they came up with backpropagation. But that didn't really take off until the 1990s because something happened in the 1990s. There were consumer graphics cards that came on the market. And it turns out that graphics cards are really good at processing giant batches of numbers. So the CPU, the main processor of your computer, can only usually operate on one small operation at a time. And if it has 4 cores, for example, it could operate on 4 operations. It does this pretty quickly, but it can't operate as quickly as a GPU can. A GPU is more like a whole bunch of different pipelines. You can do a big batch of small operations on a giant swath of pixels on your screen all at the same time. And so when we're using TensorFlow in the browser or using one of these machine learning frameworks on our computer, it's usually offloading all these calculations to the GPU saying, hey, pretend this is like 3D graphics that you're rendering and just like spit out the answers to these math problems. And the GPU is like, math? I love math. I eat math for breakfast. And it just goes at it. So number 3, when we trained a model a few minutes ago, it loaded an existing model. Like it already knew how, if you had looked at the console log on that teachable machine, if you looked at that, it would have said like loading the model is ready, it's all set to go. But we were training a model, so how exactly does that work? And this is one of the great things about machine learning is this concept of transfer learning. When you create a model that's good at something, you can retrain it and continue to train it with more data to focus it in on something to make it better. So we started with what was probably MobileNet, which is a model that was trained to identify images and objects. And it's got a lot of those convolution operations already built into it. And so what we're saying is, OK, MobileNet model, you want to now get better at identifying hands. And so I'm just going to feed you a whole bunch of images of hands, and I'm going to tell you what is a scissors, what's a rock, what's a paper. Whew. So now we understand the fundamentals. And the great news is that you don't need to completely understand everything to start. I, for one, am definitely not an expert, even though the slide that Matt showed said that I was a co-founder of an AI startup. I was not the AI scientist in that startup. I was just making the front-end UIs of this. All of this is from a lot of reading and a lot of experimentation and a lot of playing with it. But the good news is that you can play with a lot of these things without having to completely understand code. And understanding the principles behind it can work to your advantage. So how can we use it? Really quickly, we're going to look at this. Whoop. Actually, we'll come back to that in a second. So how can we use it? There are a whole lot of different machine learning platforms that you'll see. Again, I'm throwing these names up here so that you recognize them where you say, oh, PyTorch, that's a machine learning platform. And those many platforms have many different formats for models because, I mean, it's a mess of numbers, but the arrangement of that mess of numbers in a file is obviously going to be different for everyone. So Apple has something called Core ML. Windows uses the Open Neural Network Exchange format and has a bunch of things that are related to that. And the funny thing is that ONNX, or Open Neural Network Exchange, is a Linux format. Don't completely understand that. And then TensorFlow is used in Android apps and pretty much everywhere. The great news is that if you're doing TensorFlow, you can import it into Apple, turn it into a Core ML model. Vice versa, I think TensorFlow, you can generally save out to everything, and TensorFlow is kind of one of the leading tools for all of this. And we've already talked about TensorFlow a lot. TensorFlow can run on Raspberry Pis, it can run on the web. You can save out a model as a TensorFlow JS model. You can save it out as a TensorFlow Lite model to run on mobile. It can just kind of run anywhere. So that's where we're focusing today. And then when we talk about how you're programming a neural network, most of the programming is done by Python because that is a language, it's a scripting language that's pretty good for data scientists to quickly figure things out. If you've ever played with Python, it's one of the easier languages to pick up, but it's also not extremely fast compared to a native language like C or C++. And so there was an effort by Google to port TensorFlow to Swift, where you could write Swift code to describe your neural network algorithm, and then you could build on it from there, and it would run really fast, but it would also be a whole lot easier to program. But unfortunately, it looks like between when I gave this talk at the hackathon and now, Google has sunsetted it like they like to sunset a lot of things, so no more Swift. Then there are a lot of code-free tools that you can play with. Wekinator is one of the classics. It doesn't have the best UI, but it makes a little server on your computer where you feed it in data, either audio or images, and it spits back out a classification that your program can then use. And so it's used a lot by artists and musicians, and there's an entirely free college course from the Goldsmiths College in London that's online Again, the link's in this, this presentation. Runway ML is the new hotness, runwayml.com. And then there's Create ML on, if you've got a MacBook and you have the dev tools installed, there's an app that lets you play around with machine learning without code. And then, of course, JavaScript, which is letting us run all these things in the browser. So what we are going to look at next is JavaScript and TensorFlow. And what we saw before was the first version of the teachable machine. Now we're going to look at the latest version of the teachable machine, which lets you do basically the same thing. You can train a neural network model, but then the great thing is that you can download that model and they give you sample code of how to integrate this into your JavaScript projects. So you can start with an image project, audio project, or pose project. Let's do an image project. And we create our class. So we'll say scissors, and we create another one. We'll call it rock. And then let's add another one for paper. And let's just add one for background noise. OK, so we'll start with that. And we give it permission to use the camera. And now you can see this. And so we just hold to record. It holds a whole bunch of things. I'll move out of the frame. I'll move over here. I'll hold up a hand in different ways. OK, we got 185 image samples. And now let's try training scissors. And so switch on the webcam. OK, record, 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 record. Turn it towards. Do a lot of different things. And try to figure that out. OK, so we got 300 images there. We could crop the images so that it only focuses on a part of the screen. We can flip the camera to give it additional data. And so when we've got both of those, we're going to train the model. Whoops, it looks like it needs 3 classifications. So let's give it a rock. OK, so rock, rock, rock. Let's just get rid of this paper. OK, let's train the model. So this takes quite a while. But if we expand the advanced, which it looks like it's not doing, yes, a web page is slowing down my browser. If we open this up, the advanced thing lets us tune some of those settings. It lets us tell it how many epochs to go through. Now you know what an epoch is. It lets you change the batch size of how many images it's throwing through the algorithm at one time. The learning rate and other statistics you can change. And it has help functions on all of these that help you figure it out. Then it's also got under the hood, it'll show you graphs of how accurate it is as it's going, how much loss per epoch. The loss, I believe, is related to the cost function, and how many things it's confused by, etc. And then when it's done, it will give you sample code and of how to integrate this into a web app that you're making. So I'll let that crunch in the background. And we're pretty much near the end of this. So where can you learn more? If you're interested in all of this, the answer is, of course, the internet. There's a great video series from some Googlers named Nat and Lo, and then Lo moved on to a different department of Google and it became Nat and Friends. But anyway, they've got a series on machine learning that explains things in very easy to understand terms with a lot of good cartoons. 3 Blue 1 Brown is a mathematician who has a YouTube channel, and he walks through the math in such a gentle hand-holding way that it makes everything make sense, even if it's been years and years, or if you've never taken calculus. Coding Train is a wonderful YouTube series by a guy named Daniel Schiffman, who's a professor at New York University, and he's a human muppet of excitement, and he works to explain a lot of these things in really confident, clear terms. And then Kaggle, if you want to get into training big models in the cloud, Kaggle will walk you through a lot of those Python things and let you figure out how to do that. Distill.pub is a site that has a lot of interactive visualizations. There are papers that are interactive explanations of machine learning concepts. The TensorFlow documentation, there's also playground.tensorflow.org, which will let you play with setting up your own neural network. ML5JS is a project by Google and New York University to make more friendly to artists machine learning using TensorFlow.js. It just abstracts around some of the TensorFlow.js functions. And then there are other new libraries like Handsfree.js to make things like that easier. And then finally, I like to look at a lot of resources for machine learning teaching for artists, like ML for Artists is a course that was taught at NYU, and all the stuff is open source on GitHub. ML for All was a conference that was, they've got all the videos online. And Runway ML, again, all of these tools can help you use machine learning even if you're not as savvy on the code. And then, of course, we have a lot of great projects that are on our GitHub that you can check out. So to recap, this was Whirlwind. We're about to get to the Q&A. What did we cover today? Machine learning is a subset of artificial intelligence. It works by taking data and answered structured data and giving you the rules in the form of a statistical mathematical model. Neural networks are one type of machine learning model, but there are many others. Neural networks just happen to be really good at identifying things within a specified domain. And there's a lot of math. Did I mention there's a lot of math? Tensors are sets of numbers. So now when you see TensorFlow, you know that it's about a flow of numbers through a system, and Google engineers are just like, yeah, I thought up that fun name. GPUs make it all possible because they crunch giant batches of numbers all at the same time. And most machine learning algorithms and neural networks are assembled in Python, but you don't need to write code to play with machine learning. And that is the talk for part 1. Next time, we'll talk about what machine learning is good for. Why should we care? I'll be showing a lot of examples of machine learning in the wild and domains that machine learning is particularly good at or particularly bad at. If you've been doing machine learning as part of your work at Valtech, please let me know, because I might want to highlight some of it in the next talk. And that is all. Thank you very much.